Okay, so the notes are over bond enthalpy. So we're now talking about the heat and the energy of the actual bonds within compounds. Okay, so it's the change in enthalpy is the breaking of one bond in 1 mole of a gaseous substance. And we usually go with the average bond enthalpy, and it's measured in kilojoules per mole. So how much energy per mole. Something that you always need to remember, bond enthalpy is always a positive value. Okay. Energy is always required to break bonds. So if we're breaking bonds, that's energy in. And then energy is released when bonds are formed. The greater the bond enthalpy, the higher the bond enthalpy, that means the stronger the bond. That means we need more energy to break those bonds. Again, one of the key points is you take to break. You take energy to break the bonds. Okay. For example, if we have a nitrogen molecule, remember nitrogen is diatomic, and it will form a triple bond. This one doesn't look very good, but if nitrogen is triple bonded with nitrogen, the bond enthalpy of that is 941 kilojoules per mole. That means 941 kilojoules for every 1 mole of nitrogen has to be put in order to break this bond. Remember, a triple bond is the strongest bond. Versus in this dinitrogen tetrahydride compound, the nitrogen single bond that we got going on is only 163 kilojoules per mole. So there's a vast difference between the strengths of the bond, single to triple. Okay, so how we use this to estimate the enthalpy of reactions. Remember this little degree sign in this case refers to standard conditions. And then of course we have sigma here. So it's going to be the sum of the enthalpies of all the bonds that are broken minus the sum of all the enthalpies of the bonds that are formed. So when we have a reactants and then our products, our reactants are going to be the sides, those are the bonds that are broken, and the bonds of the products are going to be those of the bonds that are formed. So if we look at this, methane, CH4, I have 4 bonds. It's easiest for me personally, I like to draw out the molecules, Lewis dot structure. Sorry about that. So I like to draw out the Lewis dot structure and then look at it this way, that these are the actual bonds that need to be broken. So it takes energy to break. I always point arrows in, showing that the energy is going in. And then there's a chart that you guys will be getting that will actually show the average bond enthalpies for different types of bonds. So a carbon-hydrogen bond has approximately 414 kilojoules per mole of energy needed to break this bond. But that is only for this one. So it's also 414 kilojoules to break this bond, and to break this bond, and to break this bond. So we could say, oh, you probably can't see this because that stupid thing is there, but 4, stop moving the mouse, 4 times 414. Okay. Then we also have the chlorine diatomic molecule. And that chlorine-chlorine bond, it's a single bond. It takes 243 kilojoules to break that bond. And then there's only one of those, so just 1 times 243. Then I look at my product side. And then I have methyl chloride and hydrochloric acid. And so I look at those bonds again. And this time, when bonds are formed, we're releasing energy. Energy is released. So then I have the arrows pointing out. And it's still a carbon-hydrogen bond, so it's still 414 kilojoules, 414 kilojoules, 414 kilojoules. However, now we have the carbon and chlorine bond, and that's going to be 330 kilojoules. So 3 times 414, and the 1 for 330 for the carbon-chlorine bond here. And then I look over here at the hydrochloric acid, and the hydrogen-chlorine bond is 431 kilojoules. So I'm going to add that over here. Okay, the next thing we do is we put it in brackets, because the enthalpy of the reaction is the sum of all the enthalpies broken oh, excuse me, of all the bonds broken, and the sum of all the bonds formed. So then we just add all of that up and then subtract them. And we get an enthalpy of the reaction of negative 104 kilojoules. And remember, since the enthalpy of the reaction overall is negative, that means when this reaction occurs, it's an exothermic reaction. More energy is released. More heat is released. Okay, next we have what's called an activation energy profile. So here we have energy, and then here is just like a progression of the reaction. So it could almost be like time. We have reactants, and we have products. And then we have this thing called activation energy. Okay, the activation energy is the energy that has to go in to break those bonds. So activation energy is always going to be increased because we have to take to break. However, notice that the products is much lower here. And the reason that is because it was an exothermic reaction. Oops. It was an exothermic reaction, so the product's overall energy is less than that of the reactants. However, the actual enthalpy is this difference here. So we don't count all of this as the enthalpy, because remember, enthalpy is just the change from the reactants to the products, and so that's just this little bit here. So if we look at that same example that we did, it was 657 kilojoules per mole to break all of these bonds on the reactant side, 761 kilojoules per mole to form all of these bonds on the product side, which was a change in enthalpy of negative 104 kilojoules. So you should get, or you should have some kind of activation diagram that, or energy diagram that looks like this. The reactants being here, products being here. There's no exact like scale to measure. It's always just kind of bloop. As long as you recognize that this difference is the enthalpy, and when it's negative, the products are going to be lower than the reactants. So keep in mind, yep. So that's an exothermic reaction. This was the activation energy, so this 657 kilojoules per mole to actually break all of those bonds. So these values don't actually don't have to be shown on there. I just wanted you guys to see what it meant. So what I do want you to consider then, if we have an endothermic reaction, which means we're absorbing energy, that means our products are going to have higher energy than the reactants. So this part is actually would actually be higher than. So if you see an energy profile that looks like that, that indicates that that's an endothermic reaction. Whenever the products are lower than the reactants, then we have that exothermic reaction occurring. Hopefully this helps you guys.